Determinants. In this lesson, we discuss the determinant in both geometric and algebraic terms. Recall that a matrix can stretch, rotate, reflect, and shear an object. The change in volume of the object is given by plus or minus the determinant of the matrix. A negative determinant indicates a change in orientation. In order to develop a better intuition, let's look at the determinant for several simple examples. Because the identity matrix does not stretch or move any vectors, it has no change in the area. So, the determinant of the identity matrix is 1. The 2-1 diagonal matrix doubles the length of the sheep in the x direction but does nothing in the y direction, so the area is doubled. The determinant is 2. The 2-2 diagonal matrix doubles the length of the sheep in both the x and y directions. The area is quadrupled, and the determinant is 4. The 1-1-0-1 matrix shears the sheep, like a deck of cards, so the volume is preserved. The determinant is 1. The -1-0-0-1 matrix reflects the sheep about the y-axis. Since the orientation changes but the area stays the same, the determinant is -1. The permutation matrix reflects the sheep about the line x equals y. The orientation of the axis changes but the area is otherwise constant. The determinant is -1. A rotation matrix does nothing to the area or the orientation. Its determinant is 1. The projection matrix squashes the sheep into one dimension. The determinant is 0. A zero determinant indicates that the matrix is singular. We will return to this idea later. First, let's look at practical use of determinants as measures of change in area. Linear transformations can be used as local approximations to nonlinear mappings. Much of mathematics relies on such an approximation. By Taylor series expansion, we may view the nonlinear mapping of any small volume element from one coordinate into the other as a translation, plus a linear transformation, plus a nonlinear correction. The linear transformation is given by the Jacobian matrix. The determinant of the Jacobian matrix tells us by how much a volume element is scaled. An integral, which is a continuous sum over volume elements, includes the Jacobian determinant and a change of variables. The classical algebraic definition for a determinant comes from the permutation of the matrix elements. The Leibniz formula is the sum over the sign product of the elements, taken from the permutation group of the rows, where the sign equals the sign function of the permutations. That's a mouthful, so let's look at an example. Start by taking an element from each row and each column so long as no two elements share a row or column. Multiply the values of these elements. We get 48. Now, exchange rows 2 at a time, until the elements are along the diagonal. In this case, we need to exchange rows 2 and 4. If we perform an odd number of exchanges, we negate our product. If we perform an even number of exchanges, we don't change the sign of the product. In this case, we performed one exchange so the 48 becomes a -48. The -48 is now the first term in our series. We take another group of elements, with no element sharing a row or column with another element. The product is 96. To get these elements onto the diagonal, we first exchange rows 1 and 3, and then exchange rows 2 and 5. This time we needed to do an even number of row exchanges to get the elements into the diagonals. So the product is unchanged. We add the 96 to the series. To compute the determinant, we need to repeat this process 118 more times to get all possible permutations. A rather tedious problem to do by hand. In general, for an n by n matrix we need n factorial permutations. The 2 by 2 case is easy because there are only 4 terms. Element 1 1 times element 2 2 is 4. Element 2 1 times element 1 2 is 6, times a -1 for one permutation, so we get a -6. The 2 by 2 case has a simple visual mnemonic, the product of the main diagonal minus the product of the skew diagonal. Let's consider the 3 by 3 case. There are 6 terms this time. Luckily, the 3 by 3 case has a similar visual mnemonic. Repeat the left 2 rows on the right. The determinant is given by the sum of the 3 diagonals, minus the 3 skew diagonals. In this case the determinant is 0, although you may be tempted out of desperation to extend the mnemonic to larger matrices. Don't. It doesn't work. For larger matrices, we'll use the method of cofactors, which is a systematic approach to applying the Leibniz formula. Let's use the 3 by 3 example again. The Leibniz formula says that the determinant of the 3 by 3 matrix is sum of the 6 products of permutations. Let's examine the sum pairwise. The first pair uses the product of the top left element and the lower right submatrix. Notice that the terms from the lower submatrix can be combined as a 2x2 determinant. We call this matrix a minor. The first pair of terms in the Leibniz formula equals the product of the element 1, 1, and the determinant of the 2x2 submatrix obtained by removing the first row and the first column. We now move to the second pair. Element 2, 1 is in both of the products. The other terms come from the 2x2 submatrix formed by removing the second row and first column. We still need to interchange the first and second rows to satisfy the Leibniz formula, which gives us minus 4 times the determinant of the minor matrix. Finally, we look at the third pair. This pair has the bottom right element in common. The minor matrix, obtained by removing the third row and first column, is the upper right 2x2 matrix. Since we need to interchange 2 rows to put the elements in the proper ordering, there is no net change in the sign applied to the product. Although we expanded the determinant using the first column, we could have summed over any row or any column. Using the method of cofactors, we are able to reduce a 3x3 matrix to the sum of 3 2x2 matrices. Similarly, we can reduce a 4x4 matrix to 4 3x3 matrices, which we could then reduce to 12 2x2 matrices. The method of cofactors is still a lot of work. But, we can dramatically reduce the effort by simplifying the matrix first. Recall the elementary row operations. These operations also apply to determinants, as long as we follow some additional rules. We can interchange any 2 rows. If we multiply the determinant by minus 1, we can multiply any row by a scalar k, if we divide the determinant by k. Finally, we can add a scalar multiple of any row to any other row. The determinant of a matrix equals the determinant of its transpose. This means that all 3 rules apply for columns as well. Since we are allowed to expand using any row or any column, the strategy that we'll use is to get as many zeros in some row or column as we can. With 0 as a coefficient, there will be no need to compute the determinant of the minor. Let's compute the determinant of this matrix using the method of cofactors. A good strategy is to find a row or column that has a lot of zeros. The fourth column already has 3 zeros. Let's put another 0 in this column by zeroing out the 2 in the second row. We can do this by subtracting 2 times the fourth row from the second row. Now we have only one non-zero element in the fourth column. This makes cofactor expansion easy. 1 is the coefficient for the minor, the matrix remaining after removing the fourth row and the fourth column. Because the coefficient was taken from the fourth row and the fourth column, and 4 plus 4 is an even number, the sign of the coefficient is unchanged. Now, we choose a new row or column in which we can maximize the number of zeros. Notice that the first column is almost twice the fourth column. Let's subtract 2 times the first column from the fourth column. We now have only one non-zero element in the fourth column. We take 5 as a coefficient. The minor is the matrix remaining after removing the first row and last column. Since the sum of the coefficients row and column numbers, 1 plus 4, is odd, we need to negate the coefficient when we pull it out. Now, let's look for another row or column to simplify. The first column is a multiple of 2. We can factor a 2 out of the determinant. There's a 0 in the middle element. Let's try to eliminate another non-zero element. We'll zero out this 3. We want to preserve the middle element as a 0, so we'll subtract 3 times the first column from the last column. We now have only one non-zero element in the second row. Take 1 as the coefficient for cofactor expansion. The minor is the remaining 2x2 matrix. The 1 is in the second column of the first row, and since 2 plus 1 is odd, we need to negate the coefficient. This leaves us with a 2x2 determinant. The easiest thing to do is apply the 2x2 mnemonic. The product gives us a determinant of minus 40. Let's look at another technique for computing determinants. Pivotal condensation is a variation on cofactor expansion. Using row and column operations, we transform the determinant into an upper triangular matrix. The determinant is then just the product of the diagonal elements. Let's use pivotal condensation to compute the determinant of this matrix. The third column has a 0 and several 1s. Let's interchange the third column with the first column. Remember that any time we interchange 2 rows or 2 columns, we must multiply the determinant by -1. Computation would be easier if a 1 was in the first pivot position rather than the 4. Let's interchange the third row with the first row. Again, when we interchange 2 rows, we must multiply the determinant by -1. Now, we apply row reduction. Subtract the first row from the second row. Subtract 4 times the first row from the third row. Finally, subtract the first row from the last row. The first column has been reduced. We can now move to the second column. Let's interchange the second and fourth rows. This will make computation easier. Add twice the second row to the third row. Now subtract the third row from the fourth row. We are finished with the second column. So, we move to the third. Let's interchange the third and fifth rows. Now, we can move to the fourth column. Let's interchange the last 2 rows. The matrix is now upper triangular. The determinant is given by -1 times the product of the diagonal elements, which is 18. We close this lesson summarizing a few important properties of determinants. The determinant of a product is the product of the determinants. This makes sense if you consider the determinant as the change in the areas. Since the determinant of the identity matrix is 1, it follows that the determinant of an inverse is the reciprocal of the determinant. If the determinant of a matrix is 0, the matrix is singular and the inverse does not exist. The determinant is clearly 0 if any row, or any column, is all zeros. The determinant is also 0 if any row is a linear combination of any of the other rows.